Hello friends, in this video we are going to discuss about the diffusion capacitance of PN diode. So let us understand how the diffusion capacitance is formed inside the diode. For that, let us consider a diode in the forward bias mode. So this is the junction of the diode and this is the P side and N side of the diode. This is the metal contact of the diode. Now we have applied a forward bias to the diode, that means a positive polarity has been applied to the P section and negative polarity has been applied to the N section. Due to this forward bias, the depletion region will be very thinner in this pattern. Now this depletion region width is, let us say, W. Due to the application of the forward bias, the holes of the P side will be attracted towards the negative polarity. That is why they will flow from this P side to the N side. During this movement, the holes, when is crossing the depletion region in the N side, these holes will become injected minority carriers and the concentration of the holes can be written as in this form P N, that is mean holes in the N side at x equals to 0 can be written as P N 0 e to the power V d by V t. Similarly, when the electrons of the N side will be flowing from N to P, after crossing the depletion region, they will become the minority carriers in the N side and the concentration at this point can be written as electron concentration in P side at x equals to 0 is equals to N suffix P0 exponential V d by V t, where V d is the applied forward bias to the diode and V t is the thermal voltage of the materials of the diode. Now, due to this injected minority carrier, we can say that between this metal plate and between this metal plate, the injected minority carrier has been accumulated or moving. So, due to the injected minority carriers, a capacitance value will be developed in the forward bias of the diode, and this capacitance is called the diffusion capacitance. Because in the forward bias mode of the diode, the diffusion is the dominating parameter or movement parameter inside the diode. That is why the name is the diffusion capacitance, and this is denoted as C d. and this diffusion capacitance CD will be the junction capacitance at forward bias condition is equals to A epsilon by W, and this CD will be proportional to the root over of doping concentration. That means, as the doping concentration increases, the diffusion capacitance value of the diode will increase, because as the doping concentration means the ND value or the NA value is increased. So, the number of injected minority carrier will be also increased. Will also be increased. That is why the capacitance value or the charge content will also increase, which will in terms increase the CD value. Typically, the CD value is of the order of 100 picofarad. For better performance of the diode and BJT, CD must be small as possible. The CD value is defined by this equation. CD is equals to tau into G, where tau is the lifetime of the minority carriers, that is the injected minority carriers, and G is the conductance value in the forward bias section, and we know that G is nothing but the reciprocal of the small r, that is the resistance or the AC resistance of the diode in the forward biased. So, we know that the small value of r is equals to eta Vt divided by If, and Vt can also be written as Kt by Q into If. So, CD value can be written as tau into G, and G means 1 by R, that is If divided by eta into Vt. Now, this If is the forward current in the diode. That means, we know the value of If, that is Is exponential Vd by eta Vt divided by eta Vt. So, this is the equation of the diffusion capacitance inside the diode in a forward bias. Now, the CD value, now we can see that the diffusion capacitance CD linearly increases with tau, that is the lifetime of the injected minority carriers. So, as the lifetime increases, the CD value will also increase. Again, we can say that the CD value is proportional to the 1 by eta. That means, for silicon we know this eta is equals to 2, and for germanium this eta value is 1, and CD value is also proportional to the reverse saturation current Is, and also inversely proportional to the thermal voltage, and thermal voltage is nothing but Kt by Q. That means, it is inversely proportional to the temperature also. From this case, let us define what will be the mean lifetime of the injected minority carrier of injected minority carrier. As we know that CD, that is the diffusion capacitance, is equals to lifetime of the injected minority carriers tau into the conductance value. So, from this equation we can write tau equals to CD by G, and G value can also be written as CD eta Vt divided by If, and the units will be in second. That means the mean lifetime of the minority carrier is numerically equals to the time constant of the diode. So, mean lifetime is numerically equals to the time constant of the diode, and this is the equation for the mean lifetime of the carriers. So, we can say that CT value is nothing but the junction capacitance in reverse bias, but we know that W is equals to 2 epsilon divided by Q 1 by N A plus 1 by N D into V 0 plus V R B square root. So, CT value can be written as A epsilon divided by root over 2 epsilon by Q into 1 by N A plus 1 by N D into V 0 plus V R B. In this equation, if we divide the denominator and the numerator by epsilon, then we will get CT is equals to A by root over 2 by Q epsilon 1 by N A plus 1 by N D into V 0 plus V R B. Now, with V R B equals to 0 voltage, we can say that the Cj value or the Ct value, that is the transition capacitance value, let us assume at Cj 0. So, Cj 0 is the junction capacitance in the reverse bias mode at 0 reverse bias potential. So, we can say that Ct 0 is equals to Cj 0. If we apply Vrb equals to 0, then we can say that its value will be A by, just put V0 equals to 0. So, the equation will be root over 2 by Q epsilon 1 by Na 1 by Nd and only Vr and only V0 in farad. So, this equation will give the value of Ct0 at Vrb equals to 0 volt. Now, Cj0 can also be expressed in farad per meter square, where Cj0 is equals to root over of Q epsilon Na Nd divided by 2 V0 Na plus Nd, and this is in farad per meter square. So, we can write the value of transition capacitance Ct is equals to Cj0 divided by 1 plus V Rb divided by V0 root over in farad. So, this is the final equation from which we can find the value of transition capacitance in the reverse bias section. Now, the generalized equation for the transition capacitance can be written as Cj0 divided by 1 plus Vrb divided by V0, where V0 is the built-in potential of the diode to the power m, and it is in farad, and this m value is the grading coefficient of the junction. So, m will have a value of half for step graded junction, value of 1 by 3 for linearly graded junction, and 1.25 for diffused PN junction. Hence, in this way, by this equation, we can find the value of the transition capacitance of a diode in a reverse bias mode. So, this is all about the diffusion capacitance of the diode inside the forward bias section. Thank you.